at point A and point B. Again, I have a person at the top of a 4-meter platform that has a landing halfway through. The person starts at a speed of 2 meters per second. When they roll down this ramp, how fast are they going at part A and how fast are they going at part B? Now, before you guys launch in too deeply into the problem, we have discussed how to do this. I know you probably don't think so, but we have. In a problem like this, it is a conservation of mechanical energy problem. There is a easy to discern way of figuring out that that's the best way to solve it. And I'm going to tell you what you should write down in your notes for this. Because your test isn't going to tell you that this is conservation of energy and this is conservation of momentum and this is forces. Your test is going to ask you questions. But in this problem, one of the objects has a clear change in height under a situation where there is little to no friction. That screams conservation of energy. Because whenever there's a change in height, that means there's a change in the amount of gravitational potential energy, which immediately should make you think of conservation. So, in this problem, energy is a conserved quantity. What you need to figure out is how to use that to determine the velocity at A and the velocity at B. Give it a try. I'm going to come by and check your work in about 2 minutes. Let's take a look at how this is done. Again, we did this on Thursday, but it's been a little while. In a problem like this, the amount of energy in the system is the same at every place in the problem. Now, that doesn't mean that we know how much energy there is in the system, but we do know that the total amount of energy is the same. Consider what I mean by that. At the start of the problem, the person is 4 meters above the reference level. Gravitational potential energy is based on how high you are. So if I want to compute how much gravitational potential energy there is, I can use the fact that they are 4 meters above the reference level as a means of getting the gravitational potential energy. I don't know their mass. I know G, but I don't know their mass. I also know that at the same time, they're traveling at 2 meters per second. Okay, I don't know their mass, but I know they're traveling at 2 meters per second. This represents how much energy they have at the very start of the problem. At A, do they have more potential energy, less potential energy, or the same? They have less. How do I know? Yeah, they're closer to the ground. They lost some height, so they have less gravitational potential energy. That means they must have more kinetic energy. The sum has to stay the same. So at A, I've got mgh, where h is 2, plus 1/2 mv squared. This is how much energy they have at A. Well, the energy at A has to be equal to the energy at the start. I need to set these two things equal to each other. So m times 10 times 4 plus 1/2 m times 2 squared equals m times 10 times 2 plus 1/2 times m times v squared. Now, do you notice that every term has m in it? That's not an accident. These problems have a tendency to leave the m out because they know every term will have m in it, which allows me to factor and remove them as long as they're not 0. This is not the answer, and if I had asked for how much energy there was, I would not be able to answer it without knowing the mass. You guys aren't writing that down, but that's a good little clue to put into your notes. I didn't ask for how much energy there was. That question could not be answered with the given information. But I do have enough information to figure out how much velocity I have at platform A. The left side of this works out to be just the number 42.
Teachers and students, please pardon.
The right side of this looks to be 20 plus 1/2 v squared. All you have to do is figure out what v is now. I'm not going to do your algebra for you. V is 6.6 meters per second. You shouldn't have too much difficulty going from 42 equals 20 plus half v to 6.6. I could repeat this for part B. Part B wants the velocity at the bottom. Is there any gravitational potential energy at the bottom? How do I know? That's right. So at the very bottom, there's no gravitational potential. At the very bottom, there's only kinetic. 1/2 mv squared. That's because I'm at the reference level. H is 0. So mgh will be 0. Once I set the reference level, there's no potential energy at the reference level. Yes, ma'am.
So the H naught, that's based on the reference level?
H naught is the reference level. H naught is a reminder to us that when we are trying to measure gravitational potential energy, we're measuring it relative to some starting height. So I would say that this is H naught and this is H. So H minus H naught was 4 meters at the start. Does that make sense? Okay. Can I keep going? We good? Because there's not a whole lot to do now. This part has not changed. I don't have to look at the middle amount of energy now. I can still look at the beginning amount of energy for this problem, which is still going to be m times 10 times 4 plus 1/2 times m times 2 squared. And that has to equal 1/2 mv squared at the bottom. Meaning when I set energy equal, I can pick any 2 points to set equal. The left side of this is 42 still. The right side is 1/2 v squared. So v is 9.2 meters per second. Yep.
So basically for point B, you set the starting one equal to only kinetic energy because there's no gravitation.
Because I'm at the bottom, right. All right, we're going to do another example. I can wait, but I don't want to wait very long.
No, I was just writing something down.
Got it?
1 second.
Quickly.
Okay, you're good.
I'm good.
Yep.
Haven't been told that in a while. Great. Normally, he's done a horrible job. You're a horrible individual. All right, this next example is, it's the same idea. I'm just going to change it a little bit to try and make it more, not confusing, just to make it different. Consider I'm going to fire some projectile into the air. I'm starting at the ground and shooting the object upwards at 20 meters per second, and the object has a mass of 0.5 kilograms. I'm going to ask 3 questions related to this activity that are all considered conservation of energy questions. A, how high off the ground is it? When its potential energy is half of the total energy. Again, how high off the ground is it when its potential energy is half of the total energy? B, how high off the ground is it when its velocity is half? And C, what maximum height does it attain? Now, there are 7 minutes left. We need all 3 answers in the 7 minutes. You guys get 2 of them. Let me see what you can do in 2 minutes. If you figure out that the only kind of energy it has here at the start is kinetic, because it's not above the reference level, and it's moving, then you know the entire amount of energy that's in the system, 100 joules. How high is it when half of its energy is in the form of potential? Well, what is half of its energy? 50 joules equals mgh. Don't know where to start? Yes, we now know where to start. The total energy has to stay the same. That's how you'll answer part B and part C as well. The total energy is 100 joules. For you guys who are working part B, the object still has 100 joules of energy. No matter which part of this we look at, we know the energy that's in the system is 100 joules. At part B, the rock has gone, I don't know, we don't know how high, but it's above the reference level now, so it has gravitational potential. We know that at this point it's traveling at half the speed it started with, which is 10 meters per second. So it has kinetic. The total still has to equal 100. So I have 100 joules equals mgh, but I don't know what this is. I don't know how high it is. Plus 1/2 m10 squared. So now my job is to figure out what h is so that this sum is 100. I mean, 1/2 times 0.5 times 10 squared. How much is that? 25, which means I have 75 equals 0.5 times 10 times h minus h naught. So I assume you guys all got 15? By the way, the answer for question C is 20 meters. See if you can verify that at home tonight.